In today's lesson, we're going to look at how to find the equality of surds. Now, it's very important that you realize that everything that we're going to do today requires you to have surds, not radicals. Now, remember the difference is it's a surd if the square root of k, the square root of the number is irrational, like square root of 2, and we have a non-repeating, non-terminating decimal. So this method only works when we have irrational square roots. So let's suppose the square root of k is irrational and a, b, c, and d are rational. If a plus b, the square root of k, is equal to c plus d, the square root of k, then I know that the a must equal c and the number in front of the radical must equal the number in front of the radical on the other side of the equal sign. So let's look at an example here. So our instructions are solve for x and y given that they are radical. The very first thing you need to do in all these problems is make sure the radical that's given is irrational. So, and tell me that you've checked that by writing, since the square root of 5 is irrational, then we can apply the theorem above. So, since the square root of 5 is irrational, I know x must equal 2, and y, which is written above the square root of 5, must be equal to 3, which is written in front of the square root of 5. So that's all you have to do on this problem. I stressed enough how important it is that you do that first step, that you verify that the radical is irrational. Because if I had replaced in example 1 the square root of 5 or square root of 4, that would not be true. We would not have x equal to 2 and x equals 3. So make sure you verify that step first. Okay, example number 2. We're looking at this equality of surds. So first thing I'm going to look at is my radical of square root 11 and see if it is irrational. So since the radical of square root of 11 is irrational, then we know that w is equal to 20 and z must equal negative 6. In example 3, we're also solving for x and y given that they are rational. But this time I'm going to have to add in a little extra step. I have x plus y, the square root of 2, times 3 minus square root of 2 is equal to negative 2, the square root of 2. I need to get the variables on the side by itself. So since I'm multiplying this x plus y, the square root of 2, by that 3 minus square root of 2, the opposite of multiplying is dividing. So I'm going to divide each side by 3 minus the square root of 2. And then on this right-hand side, I'm going to use the method that we learned in the last section by rationalizing my denominator and then rewriting in the form of a plus b, the square root. So rationalizing my denominator in this case means that I need to multiply by my radical conjugate, which should be 3 plus the square root of 2. And remember, I have to multiply the top and bottom by that radical conjugate. Multiplying straight across the top, and then multiply straight across the bottom. On the top here, we should use our distributive property. That'll give us a negative 6, the square root of 2, minus 2 times 2, which could be negative 4, over, that's the difference of squares, so that's going to be 9 minus 2. So now we have x plus y, the square root of 2, is equal to negative 4 minus 6, the square root of 2, over 7. So I want to put the radical last. And now let's split up those fractions. So I can get it in the form of a plus b, the square root. And then I just need to check and see if the square root is irrational. So since the square root of 2 is irrational, we can use the theorem for equality of surds, which states that x must be equal to negative 4/7, and therefore y is equal to negative 6/7. So in this example, we're going to find radicals a and b such that a plus 2 the square root of 2 times 3 minus square root of 2 is equal to 5 plus b the square root of 2. So notice here I have variables on the left and the right side of the equation. So to work this problem, I'm going to start by multiplying the two binomials on the left together. So I'm going to make a times 3, which will give us 3a. A times a negative the square root of 2, so that's a square root of 2, plus 6 the square root of 2, minus 2 times 2, which is minus 4. And that's still equal to 5 plus b the square root of 2. Let's write our like terms together, so that's the terms with the square root and the terms without the square root next to each other. On the left-hand side, and we'll just leave the right-hand side all alone for now. So my constant, my a term, the number is 3a minus 4. And then the number in front of my square root, I'm going to factor out that GCF as square root from those second terms. And that's going to be 6 minus a times the square root of 2. So if the square root of 2 is irrational, we can use our theorem for equality of surds. So that's what we need to state. Since the square root of 2 is irrational, I can make the following conclusion. I know that 3a plus 4, which is our constant on the left-hand side, or that number a on the left-hand side, is equal to that number of 5. So I'm going to set up a new equation. I'm going to write it as 3a minus 4 is equal to 5. And now what I have written in front, multiplying the square root of 2 by on each side of the equation, we can also set those equal. So on the left hand, that 6 minus a must equal b. And so I'm going to write a second equation, which is going to be 6 minus a is equal to b. Now we're just going to solve each of these equations using our knowledge of systems of equations. The first equation, 3a minus 4 equals 5, only has one variable, so I'm going to solve for a. It's really easy to do. Now that I know a is equal to 3, I can substitute in a's value into our second equation and figure out what b would equal to. So in this case, b is also equal to 3.